When I look at the graph of a function, and I think about the y values, then I can think about what's going on the outer edges. The absolute maximum value of a function, some output for the function f of c. I don't know what c is. All I know is that f of c is bigger than or equal to every other f of x that comes out of this function. That's what it means to be the absolute highest point obtained by this graph. If I change this word from maximum to minimum, only one other thing will change in this entire statement. What thing will change? I'll flip the inequality, right? Because then I'll be talking about the value f of c that is the lowest point at every spot on this graph. Now, when I'm looking at a graph physically, just looking at the picture, this is easy. Here's a graph. The highest value is 5. The lowest value is 2. When we speak of the values, we speak of the y values coming out as opposed to the x values where those extreme values occur. So that 5 is occurring when x is 3, that 2 is occurring when x is 6. However, here's another graph. I clearly have an absolute maximum and an absolute minimum, a highest and lowest point on this picture. At A for the lowest, at D for the highest. What about B, C, and E? Consider the point E, F of E, all the way over there on the right. That's not an absolute minimum because the y value at A is lower than the y value at E. But if I restricted my picture and only looked at a little neighborhood of that point, then in that neighborhood, I would have a minimum. So if I think of this neighborhood idea, I can say the same thing at point C. In a little neighborhood, it's again the lowest point. And the same thing at point B. In a little neighborhood, it's the highest point. So if I want to generalize this idea from absolute, I can say, well, let's look at a small neighborhood. A local or relative maximum occurs at a point inside some interval. The interval is our local neighborhood. So a relative maximum occurs if I say, all right, chop away everything except this little interval around that point. And yes, that's still the highest point in that interval. At the bottom of page 276, I see another picture that actually shows the interval for each local extreme value. That little blue shaded column, a little bit to the left, a little bit to the right, around, in this case, 4, 8, and 12. Again, if I want to use a minimum instead, the only thing I'm going to do is change this inequality. So a global absolute maximum is the highest value everywhere. A local or relative maximum is in some little neighborhood. But you've dealt with these before, even just algebraically. Again, I can work from what I have already existing knowledge in algebra. Graph of x squared. What's the graph of x squared look like? My buddy, the parabola. This particular parabola, where's its lowest point? At 0, 0. I've written this now two different ways. The absolute minimum is at a particular point. I can also say the absolute minimum value is whatever the y value is for that point, and it occurs at whatever the x value is for that point. I always want to remember that when I think of a value for a function, I'm thinking of a number, the output, the y. What about an absolute maximum? I promise that's not a rhetorical question. What about an absolute maximum? Dean? Infinity is not a number. I can't use that as a value for an output. It's an idea. So is there a number that is the largest number taken on by this function? No, there isn't. Because it goes to infinity both as we go to the left and as we go to the right. I'm kind of stuck. So there is no absolute maximum for this function. On the other hand, how the hell did I pull -4, -3 out of my ass here? I've done no calculus. How did I pull this out of thin air? Completing the square. If I think about this, half of 8 is 4. 4 squared is 16. So I really want a 16. But I have a 13, so I add the 3 and I subtract the 3. Then this is x plus 4 squared minus 3. And that's a shift of 4 units to the left and 3 units down. So I have my parabola whose minimum was at 0, 0. I move it 4 units left. It's at -4. I go down 3. It's at -3. And that vertex is the lowest point on my parabola. It was at 0, 0, and now it's been moved over. X cubed minus 3x squared. Let's think about our absolute extremes. I need to have an idea of what this graph looks like. Do you know what this graph looks like? Then graph it and find out. What was that, Dean? It should go like this. There should be some wiggles in the middle, but it should be down on the left and up on the right. And if that's true, what's happening as we go further and further left? We're going downwards towards negative infinity. As we go further and further right, we're going upwards. Oh, this has no absolute extremes at all. Because this graph actually looks like this. If I've drawn it correctly. Grab your graphic calculator, make sure I'm not talking out my ass here. Yep, there it is. There's that little wiggle. But as far as I want to go to the left, I'll keep going down. As far as I want to go to the right, I'll keep going up. There's no absolute extremes. However, if I were to ask you about the absolute extremes on the picture I just showed you, I could say I only want you to look at x's between these two values. If I do that, then I'm saying you're only allowed to look in this finite piece of the graph. You're only allowed to look from here to here. Is there going to be an absolute maximum? Yeah, it'll be over here. Is there going to be an absolute minimum? Yeah, it's going to be over here. As a matter of fact, I can guarantee you there's a maximum, there's a minimum in this picture. But the reason I can say that is because I've given you this interval. If I change the interval, I could change where the maximum is and where the minimum is. But what I can guarantee is that if I have a continuous function on the interval from A to B, notice the closed interval. I have to include A, I have to include B. Then I will get a maximum and a minimum somewhere on that interval. In other words, if I give you a closed interval, I am guaranteeing that there will be some maximum and some minimum on that stretch of X values. Every time, 100% guaranteed. If you really want to know why this is true, you should take a course called The Introduction to the Theory of One Variable Calculus, where we would actually go through and prove, using formal logic, exactly why this is true. But let me do some intuitive items. Continuous behavior. When a function is not continuous, what happens? Does it mean to be not continuous? Say again? Okay, but what kind of stop do I see in the pictures? Crystal. There's a jump, or there's a hole, or there's an asymptote somewhere, right? I got all sorts of screwy things that happen when I fail to be continuous. And if that happens, then it's possible for me to have a graph. It's kind of hard to see here. There's an open circle there. That means I can get as close and close as I want to, but I'm never going to hit that value. Is there a maximum value for this function? There's no highest spot. I can get really, really close, but I'm never actually going to get there. Same thing here. This is going up to infinity. There's an asymptote here. Uh-oh. There's no maximum value. And everything I'm doing for maximums could be turned upside down to be done for minimums. If I'm not continuous, I cannot guarantee a maximum or a minimum. But if I am continuous, my continuous function forces the closed interval. Closed interval is a line section on the x-axis, right? My continuous behavior distorts that up and down. That's what the graph is. It's that interval mapped up and down, twisted and stretched and distorted, but not broken, not punctured, and not ripped apart. And those behaviors are what screws up my maximum and minimum. Damn. Okay. I know they've got to be there. I know there must be a maximum, there must be a minimum. How do I find them? Okay, let me think for a minute. If I've got a graph with a maximum or a minimum, take any of these three pictures in figure 8 here. And put your pencil in your mind at the maximum or minimum, whichever one you want to use. Here's C, here's D, there's my maximum, there's my minimum. Here, D happens to be one of my endpoints. Here, there are two C values that are tied for the maximum. But if I were to take this point on my graph and draw a tangent line, what would you know about that tangent line? Same thing if I went to this minimum point and drew a tangent line. What would you know about that tangent line? If I drew a tangent line right there, what would you know about that tangent line? The slope is 0. As a matter of fact, that's the key idea here. My buddy Pierre de Fermat yes, the same guy from Fermat's last theorem, came up with this idea. If f of x has a local extreme at some point, and the derivative exists there, then the derivative must be 0. So now let's go back and look at the examples we were looking at earlier. I had f of x is x squared. We said the local minimum was at 0, 0. The derivative of x squared is 2x. And if I put in 0, I get 0. I had g of x, my other parabola. G prime is and if I put in -4, I get 0. Ho ho! Now, please notice what Fermat's theorem does not find for me. Doesn't tell me anything about absolute extremes. It only says if f has a local extreme. Go back and look at our picture of that cubic equation. I think I see two local extremes. One is at 0, and one is at 2, and I can check. If I take the derivative of this, what do I get? And notice I can factor out a 3 and an x there, right? Because both of these numbers have a 3 in them, and both of them have at least one x. And if I do that, I'm left with x minus 2. So when I plug in 0, I'm going to get 3 times 0 times stuff. That's 0. When I plug in 2, I'm going to get 3 times 2 times 0. That's also 0. I like this idea. Knowing where my tangent line is horizontal helps. Zion. Right, because it's 3 times 2 times 2 minus 2. And something multiplied by 0 is always 0. Fermat's idea says, if I have an extreme, I'm going to get a horizontal tangent line. But wait, there's more. Fermat does not say that if I have a horizontal tangent line, I have to have an extreme. Consider this graph, this function x cubed. What's its derivative? Yes? Where is that 0? The only thing you get for an x value when you set this equal to 0 is 0 itself. So the only place I have a horizontal tangent line is 0. What's the graph of x cubed look like? Well, let's find out. Chase, what was that? There's my horizontal tangent line. But that is clearly not a maximum, nor is it a minimum. As a matter of fact, I can go a step further. Think about the function absolute value of x. What's the graph of the absolute value of x? That's my V shape, right? That's got a minimum. But that minimum is a corner. What do I know about corners? My functions don't have derivatives at sharp corners. So I really have more things I need to worry about when it comes to finding extremes. I need to know where my derivative is zero. I also need to ask, where is my derivative not going to exist? Because it's possible that I could have a minimum or a maximum there as well. If we go back and look at the statement of Fermat's theorem, if my function has an extreme and the derivative exists, then the derivative is zero. If I try and reverse that, if the derivative is zero, that's not going to guarantee me a local extreme. This is a converse error. I'm trying to draw the arrow going the other way from the if to the then. I'm trying to make it go backwards. It's kind of walking up the slide. I can't do that. So I'm going to lump these two together. A critical value or a critical number is a value on the x-axis where my derivative either is zero or fails to exist, but I have to be in the domain of the function in the first place. Think about the square root of x. Can you take the square root of -3? I'm not even in the domain, so I'm not worried about what happens over there. But between 0 and infinity, that's where I can talk about my derivative, because that's the domain. I wish I was making this function up, but I stole this right from an example out of the textbook. I'm going to run with this one. X to the 3/5 times the quantity 4 minus x. When I graph this function, I see this. I clearly have at least one local extreme, but how would I find it? And what's going on over here on the left around 0? That's some weird looking stuff, isn't it? So let's just start with the idea of finding the critical numbers. Means I need to know about f prime. So take a derivative. How do you want to do this derivative? There are lots of different options. Chris? 3/5 x, almost, negative 2/5. That's the derivative of this part. And if you're doing it that way, it sounds like you're going to do the product rule, right? Derivative of the first times the second, derivative of the second times the first. So I get 3/5 x to the negative 2/5, and then I leave this part alone. And then I leave this part alone, and I take the derivative of this part. What's the derivative of 4 minus x? Great. Here's where things start to be unpleasant. I have said on all of the derivative work we have done so far that once you take the derivative, you're done. Unless you need to do something with it. Well, here's the something I need to do with it. I need to know, where does this thing fail to exist? Where is this thing equal to 0? I need to do the algebra to simplify this. All right, fine. Let's multiply this out. 12 over 5 x to the negative 2/5 minus 3 over 5x to the, what happens to the powers here? Oof, isn't it? I'm multiplying that by that. This is an x to the first. What do I do with those powers? I add them. So 1 minus 2/5 is 3/5. Oh, that's a 5. Oh, that'll be another negative. So minus x to the 3/5. I can combine my like terms, and I get 12 over 5 x to the negative 2/5 minus 3 over 5. That's going to become 8 over 5 x to the 3/5. I don't like having negative powers and positive powers together. I'm going to rewrite this to put it on. Where does that go with a negative power? To the bottom. 12 over 5x to the 2/5 minus 8. The x here is on the top. I've got two fractions. I'm subtracting them. What do I need? So I need an x to the 2/5 here, right? That'll make that a common denominator. But the only thing I'm allowed to multiply by is 1. So it's going to be x to the 2/5 over x to the 2/5. What happens in the numerator of that fraction when I multiply those together? Exactly. Because it'll be x to the 3/5 plus 2/5, that's x to the first. Which means I get 12 minus 8x over 5x to the 2/5. That's my derivative. That was a lot of messy, ugly algebra. It wasn't calculus that was the problem. It was the algebra that sucked. This is going to be a common theme in all of your math courses. It's what you did last time that's the hard part. Because I assume you know how to do algebra. We're just going to learn how the calculus deals with it. The algebra sucks. I need to know two things to find my critical numbers. I need to know where my derivative is 0. I need to know where my derivative fails to exist. A fraction is 0 when the top is 0. A fraction doesn't exist when the bottom is 0. So I can now say that I know f prime of x is 0 if the top is 0. And I can say that f prime of x will fail to exist when the bottom is 0. What x value makes this first statement true? Similarly, in the bottom, if I divide by 5, I get x to the 2/5 is equal to 0. The only way that's going to be true is if x is 0 itself. If my function has a derivative that doesn't exist, that means my tangent line has a slope that doesn't exist. So either I have a corner or a vertical line or a hole or a gap or something like that, right? There's a vertical tangent line right there when x is 0. And at 1.5, I'm at that local maximum. It worked. I was able to find my critical numbers and use them to identify my extremes. How do I know these are the only extremes possible? Go back to the intermediate value theorem. If I had another extreme, it would either be another maximum or another minimum, right? Think about what's going on as we go over here on the left. From this picture, it looks like this graph, as I go to the left, is going down. If there's a minimum somewhere, it's going to have to turn back around and start coming up. That would be another place by Fermat where I would have another 0 in my derivative. And we only had 1. Same thing over here on the right side. It's going down as I go off to the right. If there was a minimum somewhere, I'd have to turn around. These are the only places. Questions? I've left something out. Going back to that original idea with the x cubed function, x cubed minus 3x squared. This function had an absolute maximum and an absolute minimum. But it also had 2 other locals. If I say, hey, I want to know where the absolute maximum and absolute minimum are on this interval, notice that neither local extreme is the absolute extreme. Between -2, whoops, -2, and 4. The lowest point is at x equals -2, y equals -20. The highest point is over there at 4 with y equals 16. I'm not going to find those if I just look for critical numbers. So here's the additional statement. Since I am on an interval, the endpoints come into play. And what I can say is that what you want to do is actually build a table. Notice, Zion, if I set this equal to 0 with the derivative written out like this, well, then either this piece is 0 or this piece is 0. So those are my critical numbers, 0 and 2. But I also have the numbers that are the endpoints of the interval. So now, all I really need to know is what are the y values? And we already computed those. There's my absolute minimum. There's my absolute maximum. So when I'm dealing with an absolute and I am given an interval, all I have to do is make a table. When I'm not given an interval, I'm going to have to do a lot more work. We'll figure that out next week. I will tell you that I have two things stuck in my head that I wanted to make sure you heard. The first is that if I go back and just look at the graph of x cubed, that's the graph of x cubed, right? And we said at 0, that's not a maximum, that's not a minimum. I want you to picture this like the neck of a horse. I'm going to call that a saddle point. It's not a maximum, it's not a minimum, but I can sit there. It's flat. So that's a saddle point. To that end, remember I told you about that calculus, the musical thing? Every time I do this, I hear the can-can. Saddle, peak and drop, and saddle, peak and drop, and saddle, peak and drop, and peak and drop, and peak and drop. I'm trying to find a maximum or a minimum. For a minimum, just take derivative and happy. It's not just assessed 0, 0, 0. This song's been stuck in my head for a decade, people. Every time I do maximums and minimums, I see the little dancing line. The can-can. But it works. What do I need to do? I need to take a derivative. I need to know it's 0. But over there in the back, it says local maxima are on an interval. Local minima are on an interval. I need the intervals, the little neighborhood to do locals. I hope it gets stuck in your head too. It'll help. Our exam is Monday. The keys to the review sheets and the homeworks are getting posted right now. If you still have your homework, I need it. We'll see you all on Monday.